let me just put this up here. Yeah, I got carried away. Sorry, guys. Okay, so what we want to do is part 2, frequency encoding. No, it's my fault. I just got carried away. I was somehow... Okay, we can start up number 2. Okay. Okay, so now we'll leave behind the off-resonance nightmare and try to get an intuitive picture of how frequency encoding actually works. And this is probably the most important lecture for really understanding how MRI imaging works. So, and trying to understand it really in a concrete way, like what's actually going on with the spins in brain space. You know, what are we doing to the spins in the actual brain? So one of the things, when we talked about this, we already talked about it before, but I just want to go over this. I talked about it in the graduate session, but I want to go over it again. About how did MRI sort of get off the ground? And the original concept of MRI was basically an analogy between a gradient and a chemical shift. Jeez, cannot smell. So here's spectroscopy, difficult word to pronounce, and here's imaging. So this whole thing is an analogy between kind of like, you know, Darwin and an analogy between artificial selections, you know, selecting crops and plants, and natural selection, something like that occurs in the wild. This is the sort of the origin of MRI. It's an analogy between spectroscopy, chemical shift, and imaging. And so how does the analogy go? Well, we've got chemical shift, and then over here we've got a gradient. And then we stimulate with RF, and we do the same over here. And then we get back time-sampled FID. Containing multiple frequencies. And the same thing happens over here. And then what's the final thing? We do a Fourier transform. FT to get frequency peaks. And then what do we do here? We do the same. And so you can see there's an analogy between FT to get image. So whenever you look at an MRI course, they always start with this because it's sort of intuitively sensible. Chemical shifts. We got gradient cause shifts, so that all makes sense. And then we stimulate with RF, that's the same. We time sample the FID that's coming back with the gradient on, same. And and there's multiple frequencies in there because there's different resonant frequencies in there. And then we do a Fourier transform. And we analogize frequencies, precession frequencies, with spatial locations. And so the last step is the problem. The last step is the problem because in spectroscopy, what we've got, here's our signal. So our signal is basically, samples of oscillations in the time domain, because we're actually, we're actually looking at these different protons, and they're oscillating at different frequencies, chemical shift. So that's our signal. And then when we do the FT, we go from the time domain to the frequency domain. So now we're in the frequency domain. And so when we're in the frequency domain, what do we get? We get those, different frequencies. That's frequency, plotted that way. So we see these little peaks of different frequency, and those correspond to just fishing out the time signal that came out of these overlapping. So you've got like two protons, and one's going rapidly and the other one's going slower, and then they're generating two overlapping signals, and the Fourier transform fishes them apart, and you get like two peaks. So why is that a bad analogy for imaging? And so what I'm saying is that if you start thinking of it this way, imaging this way, you'll get stuck. It's a garden path, so don't think about it that way. And why don't think about it that way? Because in imaging, what we're doing is we have samples, so we're sampling the FID, but we have samples of spatial frequency. We have spatial frequency like this. Samples of spatial frequency domain. And what are we doing? We're doing an inverse Fourier transform. We're doing an inverse Fourier transform. And then what we're doing is we're getting our spatial object. Oops. So why does the analogy sort of work? It sort of works because the inverse Fourier transform is the same as the forward Fourier transform. That's the trick. Because those two are mathematically very similar, it is true that we're turning on a gradient and we're stimulating with RF and we're doing a Fourier transform. But because the inverse Fourier transform is the same as the forward Fourier transform, we don't realize that conceptually we've done the exact opposite. So here's the frequency domain over here, but the frequency domain is there. It's on the opposite side. And so this was first realized in the 80s, after MRI already existed. It's kind of funny. It's just like people just sort of slept walk through inventing MRI, starting up companies, making machines, but they didn't really fully sort of conceptually understand what they were doing until later, when we had this, the K-space perspective. And what is the K-space perspective? The K-space perspective is that here's the frequency space. That's like K-space in spectroscopy. You start off with oscillations in the time domain, and then you go to the frequency domain. The K-space perspective, it's like a Copernican turn. The K-space perspective is that actually your sample is not time domain. your sample is actually spatial frequency domain. It's a frequency domain. And then when you do an inverse Fourier transform, you get back to the non-frequency domain, which is the spatial object. And so that's why there is no frequency encoding. So there is no frequency encoding. Don't think that way. So encoding, it's all phase. It's all phase. So let's just do frequency encoding as phase encoding to get a concrete picture of what we're actually doing to the brain and why it has nothing to do with sort of unmixing a bunch of samples, a bunch of signals that are at different frequencies mixed together, like what we're doing when we get a spectrum from spectroscopy. So let's just look at this. Look at this with a concrete picture just in 1D of what's going on to the spin phase and why the spin phase is basically spatial frequency. Okay, so let's start by turning on a gradient. So I'll put the gradients over here. So before we've turned on the gradient, so right before we turned on the gradient, we did the RF somewhere back here. So we'll put RF. So let's look at what happens right after we did the RF. Okay, so that's our first time point. So basically what happens is let's just take a one-dimensional picture. So here's just X, the X direction, and at each point in the sample, and so that you can sort of think of this, as just like, here's a brain, and we're just looking at one line across the brain. And so what does that look like? That looks like something like this. Okay, so that's our brain. So we're just doing a one-dimensional version of the brain, which is that it's light here and dark here and dark here. I made my brain too big, sorry. It's dark here. So it's dark here and light here. Dark. So keep that in mind. That's our picture we're going to do. So when we do the RF pulse, what does the RF pulse fundamentally do? It bunches together all the rotating protons so that their phase is all the same. That's the definition of an RF pulse, because remember, if we just let the FID decay, their phase eventually just spreads out into a disk, just a uniform disk, and there's no signal. So when we do the RF, what we do is we bunch the protons together so that they're all precessing with the same phase. And so we have to draw that. So I swear to draw it bigger. Okay, so here's a little phase circle for all our protons. And so if we look at I'll draw it better this time. So they're all at 0 degrees. So here's our proton. I'm drawing the transverse plane flat, so we can look down on the So if we look down on the transverse plane, we would see that they were all lined up with each other. So that's what the RF does. So that's one. It's the RF. So now what happens? We turn the gradient on. So here's 2. We turn the gradient on. So this is time here. So now we're looking at, so the point in time we're looking at is after the gradient has been on for a very small amount of time. So let's just look at it over here like this. So now we're at this point in time. So we're still, so this is time over here, this is space. Okay, so now we turn the gradient on for 1 unit of time. Now if we if we've arranged everything correctly with the strength of the gradient and how long we had it on, so really we have to consider two things, is like how tall is the gradient and then how long do we leave it on. But let's assume that we set everything up so that basically we wrapped up the spins one cycle. So what does that mean? It means that let's assume for the sake of argument that this is the left side of the this is the the 0 point in the gradient. So no effect there. And then what happens is about halfway through, we will have wrapped up this guy to 180 degrees, and then all the way through we're back at 0. So what will happen in between is you'll see, the vectors will all be sort of like this. And now they'll be slightly down, and then all the way down, and then to the right. Okay, so that's the state of affairs at this point in time. So we essentially kind of wrap these guys up to exactly one cycle ahead. Okay, so now what do? We record a snapshot, and that's the critical point to really wipe your mind clear of sort of like multiple frequencies coming into the receiver. That's irrelevant. We record a snapshot of this. And what is a snapshot? It's just what we said when we talked about the vector, when we talked about the signal equation. It's a vector sum of all these guys. It's just a vector, so that's what the RF coil picks up. It picks up a vector sum of the local transverse magnetization. So this is, local MT. And so, when we do the RF coil, what does that do? So this goes through the RF coil. And what does the RF coil do? Along with the phase sensitive detection, blah, 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 it just does a vector sum of all local MTs. So it just sums those guys up. Now, if you're looking at that, you might think, wouldn't that add up to 0? And yes, in fact, it would, if you had the entire bore filled with gelatin. So you probably weren't expecting me to say that. So if we just filled the entire bore with gelatin and turned on the gradient, the signal coming out of all these things would be exactly the same. And since they're evenly distributed around the circle, when you add them all up, you get 0. So that sort of seems unenlightening. So what's going on? Well, what's going on is there's actually a brain in there. And so there's this thing in there. So there's basically not very many spins here, because remember this is X. This is X here. So there's not very many spins here. And then there's a bunch of spins, because that's the brain. And then we're off to the edge of the brain, not very many spins again. So what does that mean? That means that the local magnetization vector that you get from here is going to be very small. So in real life, what it is there's like a little tiny guy here, tiny guy here, tiny guy here, tiny guy here. And now we've got suddenly a much bigger one, and a bigger one this way, and a bigger one that way, and a bigger one this way, and a bigger one that way, and a bigger one that way. And then, small again, really tiny, really tiny. So what happens when we add these guys up? So if we add these guys up, what are we going to get? We'll get a bigger vector. So the up-down parts will cancel out. We'll basically get something like that. That's the M vector. It'll have about 180-degree phase, and it'll be quite big. That's also known as a Fourier transform, because what we're doing is we're taking something that's basically sines and cosines. It's a complex number, even though it's an actual brane with spins in it, but it's a complex number, and we're correlating it with the brane across space. So basically what that is one term in the Fourier transform. We've got some sines and cosines here, and then we've got a brane that we're weighting those sines and cosines with, multiplying them by sines and cosines. And then there's the Fourier integral, that's just a sum, like the RF coil. So the RF coil is just summing across this whole mess, and it's giving us one vector, one number. So if you look at the left side of the Fourier transform, is basically just, a single number. How much of this frequency is there? But what frequency is it? It's a spatial frequency. So what it is the spatial frequency across the brane. And so if we go back to our image of the brane, what is the biggest spatial frequency in the brane? So here's a brane. What is the biggest spatial frequency in the brane? Well, the brane is here, and then there's like black around it. And so what that corresponds to, if we graph it out, is, black, and then brane, and then not brane. So we can think of that as a spatial frequency. It's basically a variation across space, just like you would think of variation across time of a time signal. And what does it correspond to? It corresponds to, something that looks something like a sinusoid, like that, like an upside down cosine. So what is the biggest spatial frequency in the brane by far? It's one cycle. So, what does 2 cycles look like? 2 cycles would look like a sinusoid with, 2 bumps to it, like that. And does the brane look like that? It does a little bit, right? It sort of looks a little bit like that too. Not as much as it looks like 1 cycle. It looks more like 1 cycle than it looks like 2. So this is, this guy is, K equals 2. This guy is spatial frequency equals 1. So the biggest one is, this is M for K equals 1. Okay, so that's the critical thing, is that forget about all the frequencies, the precession frequencies. Don't think about the precession frequencies. What you're doing is you're taking a snapshot. You're taking each data point is a snapshot of the transverse magnetization vectors all summed up. Complex valued vectors all summed up. And you've got, so this is the snapshot. So this guy is a snapshot equals 1 k-space point, data point. And it's a big one because there's a lot of spatial frequency 1 in the brane, because it's a big blob and it's got black around it. Okay, so now what do? We just leave the gradient on. And so if we leave the gradient on, so here's point 3. So now we just leave the gradient on, and let's leave it on for, I'll just do 2. Okay, so leave it on for 2. So instead of here, we're just going to leave it on for 2 units of time. And now consider the situation. So now what will happen, we'll just have 2 wraps. So there'll be same picture before. So this is looking at the direction of the transverse magnetization. And then here's all our magnetization vectors. So now it's going to be going that way. And then halfway through, we're going to be back to where we started, and then all the way through back to where we started. And then halfway in between here, we're going to be up this way, and then halfway in between here, we're going to be up that way, like that. So now we're heading up like this. Oh, sorry, screwed up again. Didn't get my vectors correct. I didn't put the reversed ones in there. That's not up. This guy's going to be that way. In the middle, we're going to be going that way. So now you can see they're wrapping faster. We're warping them into more. Okay, now I've got it going right. So now you can see they've gone around twice. Okay. So if we plotted the phase of those guys, phase angle, you would see what happens if this was if this was 0 and this was 2 pi, equals 360, the phase would be unchanged here, and it would slowly ramp up like this until it got up to 2 pi, 360 equals 360. So that's spatial frequency 1 wrap in phase. And so what does the phase of spatial frequency 2 look like? It still goes up to 2 pi, but the phase angle, it's just this angle. I'm just plotting this angle right here, the actual sort of angle of the arrow. So what it looks like is it gets all the way up to 2 pi here, and then it goes back to 0, which is equivalent to 2 pi, and then you're all up to 2 pi again. So this is the phase at this time point. So we've just gone around the circle twice. And so, what happens then later on? Well, there's just more of the same. So if you want a very high spatial frequency, like for instance to distinguish between gray matter and white matter in one gyrus, you're going to need much higher spatial frequencies. So after you leave the gradient on for a long time, I didn't draw my gradient wide enough, but if you left it on for 128 units of time, then you'd end up with the phase wrapping up a whole bunch of times like this. It's harder to draw, so I'm just drawing the phase picture. So it would just, so you would have a whole bunch of wraps across the image. So that means that, et cetera, when we get to the end here, this guy is actually 128 cycles ahead. And that was understanding this, how many wraps there were, is what finally sort of got it into my head how this works. So you do the RF. So this would be like, for, we'll put a little dash here because my gradient is longer. So this would be like at the end of the gradient. So at the very end, right here, you can see you'd have 128 wraps. And what is that? That's spatial frequency 128. And how does it work with the brain? Well, you've still got that same brain in there, but that brain's got like gray matter and white matter and gray matter. There's little variations in the brightness as you go across the brain. There's gray matter and white matter, gray matter, white matter. So, and when you correlate it with this, basically, you sort of like see how much does it correlate with a sine and a cosine, also known as an arrow going around the circle. So from this, you can see there is no frequency encoding. And what is the most critical way of showing that you're not doing something like spectroscopy where you actually have to pay attention to these multiple resonant frequencies that are being emitted by the sample. And the most clear way that I could think of really sort of driving that home was to just consider somewhere here. I didn't include that page. Yeah, I don't need that page. So let's consider this. So when you turn the gradient on, as soon as you turn the gradient on, you actually do get multiple resonant frequencies happening. So you might think that if you're recording data, that it really depends. So here's your data points like this. And here's your echo. If we've done a reverse thing, and here's your echo coming. That's the amplitude of that graph indicates how big a data point you get. It's complex valued, but whatever. So you might think like during this time, there are multiple frequencies. That's true because we turned a gradient on and we started messing with the high end of the gradient because this guy's that's the reason it got ahead for this snapshot is that it was precessing faster. So it is true there are multiple frequencies in there. But just consider this. What if we turn the gradient on like this and then we turned it off? And then we turned it on for another unit of time and turned it off like that. And then what if instead of recording a snapshot with the gradient on, instead we recorded a snapshot with the gradient off? So in that case, what's going on? You've got multiple frequencies here. Here. All same frequencies here. What would happen? You get the same data. There'd be some decay, but let's just forget about the decay. The data would be exactly the same as if you recorded with the gradient on. So that's the most critical thing. So same as above. So that means that not necessary to have multiple frequencies on when recording data. So it's not, don't think of it like spectroscopy. It's not, the Fourier transform is not fishing apart the frequencies. It's not fishing apart the frequencies that are being like multiple protons precessing at different frequencies, and somehow you do a Fourier transform and you sort of make a frequency spectrum and you sort of turn it back into individual frequencies. That's not occurring because otherwise this wouldn't work. This wouldn't work because here you're recording all the data with the gradient off and the frequencies are all the same, but you still get the same data. So really the critical thing is what the different frequency of precession has done to the phase. And instead of sort of thinking of it as sort of disentangling different frequencies, instead think of it as we put the gradient on, the gradient messes with the phase. After 1 unit in time, we have basically spatial frequency 1 in phase. And these are actual physical phase stripes across the brain. So if you actually think of it, it's a concrete thing. You know, it's if you've got the brain, I just drew it in 1D here, but if you draw it in 2D, you know, here's a picture of the brain. We'll draw a coronal slice. There's a picture of the brain, stuff in the middle of the brain. What have you done? You, in the case of, say, spatial frequency 2, so this is, you know, this guy is spatial frequency equals 1. This is spatial frequency, you know, K equals spatial frequency 1, K equals spatial frequency 2. This is K space equals spatial frequency equals 128. So if we did 2, what would it look like? Well, if we did 2 in the x direction, say, what's going to happen is there'll be, you know, 0 spatial frequency here, and then gradually, usually draw it the other way around. Let me just make sure I draw it the same as I usually. Yeah. I think I draw it dark for low. Okay, so basically the phase will be low, will be like about 0. I'll do this one. And then the phase is going to be increasing, getting lighter. And then when you get to here, it will wrap around. And so now it'll sort of like wrap around back to 0 again. And then it will be getting, you know, lighter like that. So if you look at the, you know, if you looked at a graph of the phase, you would see it went from 0 up to 2 pi and then 0 up to 2 pi, like that. So what you've done is you've physically stamped on two stripes onto the brain. And then when you do your, you know, your RF coil, you just sum across the whole thing. You know, integrate across the whole thing. This is the RF coil does that. And then what do you get out of that? You get some vector, single vector, one data point. It's got you know, a real and an imaginary part, but basically it's just a single data point. And that single data point says, how much does the brain look like 2 stripes? And it sort of looks like 2 stripes a little bit. And you know, it looks more like 1 stripe. When we put 1 stripe on, it looks more like 1 stripe. So that's frequency encoding. So it's phase encoding. Phase encoding is exactly the same as frequency encoding. No difference between frequency encoding and phase encoding. The only difference is what direction the gradient is being applied, but it's exactly the same concept. So a lot of times in an MRI course, they'll give you the spectroscopy analogy, and that sort of seems understandable, and then they talk about phase encoding, and it's just like everything's out the window, it doesn't make any sense at all. And the problem is they're trying to sort of ease you in, but what they're actually doing is they're sending you into a garden path. So when you just start from the beginning and say frequency encoding is just phase encoding, you could say phase encoding is just frequency encoding. They're both the same. All they're doing is they're using a gradient to stamp on these phase stripes onto the brain, and then they're collecting individual terms of a Fourier transform. And the individual terms of the Fourier transform are how much does the signal correlate with sines and cosines of frequency 1? That's 1 point, complex point. How much does you know, the sample correlate with sines and cosines of frequency 2, another complex data point. Complex data point just meaning like a vector. So, and then you can see from this demonstration that multiple frequencies are not required. They're required in order to mess up the phase, but you can record all the data with the gradients off, in which case all the frequencies of precessions are exactly the same and you get the same data. So really the frequency isn't the focus. The focus is what did the gradient do to the phase? That's really where you should put all your sort of mental effort. And so I'm going to stop a little early this time so we can take some questions hopefully, because this is if you can understand this, then basically you're over the hump. You can sort of understand how MRI works, what K-space is, how does imaging actually work. Okay, David, we can stop recording there.